be presenting work mainly on the Azores. A lot of the work's been done actually by Yu-Chun Chang, who's online with us. Hopefully he can answer some of the questions at the end. But there have been a large number of other contributors to this work, so I'm acknowledging them with this slide you see. I won't go through individual names. You'll see some individual names as we go through the talk. Is it going to let me forward? How strange, doesn't it allow you to forward with a... That's okay. So firstly, thank you for inviting me to give this talk, but also thank you for supporting our working group on seamounts and islands near mid-ocean ridges. So I'll just say a few words about this working group and our workshop. Why should anybody be interested in seamounts and islands, and why in particular should InterRidge be interested? InterRidge has been mainly focused on spreading centres up until fairly recently. Seamounts are interesting, partly because there are so many of them. This is a census carried out by Paul Wessel over 20 years ago now, and he estimated over 100,000 seamounts exist that are more than 1 kilometre tall. So I suspect that means that they could be the most common landform on Earth, but they're all hidden underwater. I did a nice experience of writing a review of seamounts. Most of the seamounts you see here are volcanic, but some are produced by tectonism, i.e. faulting, and some are actually giant landslide blocks as well. Seamounts are interesting because they also are places where a lot of fisheries are concentrated, and in the future maybe they're sites for mining exotic metals, perhaps, and so there's all the environmental impact of that to be worked out. Volcanic islands are interesting to many of us as geologists, but they're also big impacts of geological events, and that's illustrated by what we saw in La Palma last year. The lava flows and other volcanic products severely disrupted one side of the island, but it illustrated how sensitive these communities are because it can affect air travel and sea travel as well. So it can have an outsized effect. This was also illustrated by Iceland. A number of years ago, there was an eruption on Iceland and it caused a shutdown of air travel between Europe and North America. So these places are very small, but they can have enormous impacts way beyond them. And this, of course, was illustrated just on Saturday. We had the submarine eruption. It wasn't at a spreading center as such. It was on the island arc, but it's very close to a back arc spreading center, and it's had impacts around the Pacific in terms of the tsunami. And geological events can include landslides as well. So this is in the Hawaiian Islands, we have the very big landslide blocks. They are known to have caused tsunamis in the past because we have deposits from tsunamis on adjacent islands. These are probably not very frequent. So this is the frequency for the Canaries that Sebastian Krastel worked out many years ago, maybe 100,000 years or more frequency. So if you consider how many island groups there are in the world, this may suggest these big landslides probably happen once every 10,000 years, very, very roughly. That's not so frequent. So the effects would be very dramatic, but maybe they're not so frequent. What's less well known, and there's a hint of it in this image, you can see this gullying of the upper slope of Oahu. Could these be produced by landslides? In which case there are many, many of these gullies. Here's an image of Terceira Island in the Azores, produced by Yu Chen. And we're looking towards the island, into the upper slope, and the colors represent gradients in degrees. And that's picking out side walls and head walls of landslides. There are many, many more of these compared with the big landslides. So maybe they are a risk just because they could occur much more frequently. And earthquakes. Earthquakes affect mid-ocean ridge islands perhaps disproportionately because they lie near plate boundaries. The Azores especially lies between Eurasia and Africa, and they experience frequent earthquakes. So 1998, Fayal Island had a magnitude 6. This is not such a big earthquake, but the buildings aren't constructed to cope with shaking associated with such an earthquake. And so there was quite a lot of damage and injuries as a result. You can evaluate these the risk of these earthquakes looking at faults on land, but of course a lot of the faults that are potentially active are underwater. So we're missing a lot of these escarpments we see in multi-beam data. They could be active faults. We don't know. They've not been evaluated. And again, earthquakes also have present problems for how you respond to them and help communities when they get affected. So we came together as a group to form in a workshop. And so I must thank, besides the InterRidge, I thank the SCORE because they provided 3 scholarships for developing country scientists to come and join us, and the Institute of Hydrography in Lisbon, who were a wonderful host and provided a lovely venue as well. So it was an extremely enjoyable experience having this workshop, and with a very wide range of expertise encompassing biologists and oceanographers, geologists, remote sensing experts. And our discussions illustrated in these environments, quite often a lot of our work is very multidisciplinary because we have to share resources, have to share the ship, and some of our data sets are shared. And so that's quite a feature of work in this area. There's a copy of the report on the InterRidge website, I believe, and I've also put a copy on ResearchGate. So if you search on the name of the workshop up here, you should be able to find it, and I hope people will be able to take the time to take a copy and look at our recommendations. So coming back to this image, we're looking at the side of one of these volcanoes underwater. We're going to look at the landslides, the embayments to begin with, and later on we're going to go down slope to look at the deposits that have been left behind, resulting from these landslides possibly. So we're going to go from the top of the slope down to the bottom of the slope, if you like. When you see an image like this, perhaps it prompts a number of questions like, what is the basic material that underlies this slope? Is it strong or is it weak? And that might dictate how we interpret these features. What are the geometries of these landslides? Can that tell us something interesting? How big are they? How many of them are they? I said that there are many more than they are the very big landslides. What, by how many orders of magnitude is that the case? Do they produce tsunamis? That's obviously an important issue to resolve. And how frequently would they produce tsunamis? How frequently would they fail? Would they be a significant threat to local communities or not?
Oh,
so I'm going to look at the slope materials to begin with. And this is a difficult thing to address. If you look at the gradients in here, it's very steep. They're not, we haven't, unfortunately, got any coring done. And it would be difficult to do anyway because it's very steep. And likely the material is very heterogeneous. We suspect a number of sources of the sediment is being exported from the shelf, and that's what we're seeing. So firstly, volcaniclastic material from erosion. So this is perhaps an extreme example. This is Kapalinos when it erupted in 1957, initially erupted in the sea and grew to form a coastal cone like this. This provided a nice example of erosion that we studied. Zhongwei Zhao led this study in 2019, where we looked at how the coastline changed with time. And erosion is sped up in this situation because the material is quite weak. There's no shelf initially, and it's exposed to the Atlantic waves. So initially, erosion was extremely rapid, and over time, it declined. And you can't see it in here, but actually declined in an inverse power law, fortuitously, I think. But anyway, an inverse power law decline. So there's a lot of material released by coastal erosion. And at the back here, you see tall sea cliffs. A lot of the Azores have very high sea cliffs. And that means that any meter erosion distance of the coastline generates a lot of material. And so we think most of the material reaching the shelf comes from coastal erosion. Rui Quarto did a study looking into that for Fayal and concluded that most of the material is from coastal erosion. Some of it may be subaerial. So down here, I'm showing an acoustic backscatter map. Fernando Tempera collected these data for his PhD. This is the coastline of Fayal. And the sonar data shown low backscatter, a light gray, and high backscatter, a dark gray. And what you see are these low backscatter ribbons that cross the outer shelf. In this case, a very large, it's actually a fan. You can see the 50-meter contours bowed outwards. We think these are effectively the sand being transported either from coastal erosion or from maybe some subaerial erosion and being fed out towards the outer shelf. On the slope, we see evidence of many sediment waves. So this is a gradient map. You see all these, and this roughly corresponds to in here. You see there are many sediment waves, which suggests transport of material in sedimentary flows down the slope. And grab samples on the shelf have revealed some carbonate material as well. So we have biogenic production, and we have these various products of erosion. And possibly during low stand conditions, you may have had lavas reaching the shelf edge as well. So to answer the question of what underlies the slope, I can't tell you quantitatively what underlies the slope, but there are likely to be all these different materials there. So to look at the landslides, our data aren't perfect. There was a poor mounting of the transducers for the survey, but you can see some landslides are really well defined. You have sidewalls and headwalls. Some are much less well defined. You may have only light depression. And we interpret this variation as due to later these sediments coming from the shelf are depositing on older landslide scars and gradually obscuring them. So Yuchen has classified the scars. Class A is very clear, Class E much less clear. When you look at the volumes of all these scars plotted against area, you notice there is a nice correlation. The exponent is 1.3. If you expect landslides as they get bigger to also get deeper in the same proportion, this exponent should be 1.5. And it's not quite that. It suggests that there's an impediment to deep failure. So there must be some resistance to deep failure. For example, the material may be compacted, or there may be cements that are holding the particles together, or there might be some bedrock underneath or some kind of more solid layer. So Yuchen's identified more than 1,000 of these valleys. There are an enormous number of them. Many of them are likely due to these landslides. But this, I think, is this is a curious observation, and we think it may have wider implications. When we look at the volume normalized by the slope area that we're studying, Fayal and Pico have relatively small landslide cumulative volume. So add up all the volume, divide by the area, you find it's fairly small compared to Saint George and Terceira. Terceira Island and Saint George seem to have quite big landslides, and on average, less of them. So an interpretation of this is that on Saint George and Terceira, perhaps there's a longer period between big earthquakes, and that allows more sediment to build up. And then when you do get a big earthquake, assuming these are all earthquake triggered, you get a bigger landslide. Whereas on Fayal and Pico, more frequent earthquakes prevent the buildup of unconsolidated sediment. And there's also another possible effect of densification of the sediment produced by the ground shaking underneath Fayal and Pico. If we're right, and we don't have any other evidence to back this up, it's purely looking at the landslides, it means that these two islands, Fayal and Pico, have a higher risk of big earthquakes than Saint George and Terceira, which is not something you would say from looking at the earthquake maps. These are the historical earthquakes in yellow. There's no obvious pattern in them. And the fault breaks on land don't suggest particularly a bigger risk, or there is a very large fault potentially across Pico, but it's not obvious. So what we have done here is calculate a shake map based on the record from instrument recordings of seismicity in the Azores. And we're taking data from the ISC catalogue. We calculate the ground accelerations from each of these individual earthquakes and applying standard attenuation relationships, and take the maximum and see most of the seismicity has affected Saint George. This just reflects two big earthquakes adjacent to the island, and only the one near Fayal. So the pattern is, this is almost certainly not the long-term pattern. If you look at the bathymetry, there are faults everywhere. So this is very unrepresentative, and certainly the Azorean or Portuguese researchers looking at seismicity don't just take the historical seismicity. we're suggesting that there could be a large risk underneath Fayal and Pico. It could also mean that we could do this in other island groups and maybe get some information about earthquake risk or whatever is triggering these landslides. I'm plotting cumulative distributions, complementary cumulative distributions. So when you get back up to 1, it means you've counted all the landslides, and we're looking at their relative volumes. The Azorean population of landslides has a very steep slope, relatively steep slope, which suggests we're not recording many big landslides. We're mostly recording many small landslides. So that looks quite different from the Tyrrhenian Sea, which does have some quite big landslides. But the shape of the distribution, if you weren't concerned about the scale of a map, it would look kind of similar to maybe some of these other areas that also have very steep distributions. So the next question, could these actually produce tsunamis that we should worry about? There have been tsunamis recorded in the Azores that are difficult to associate with earthquakes. So they might be due to landslides. Well, to do this properly, you'd need to model individual landslides, and that's not something we've had time to work on, and we don't have the expertise to work on either. So we've appealed to a set of empirical relationships that Watts produced. What he did was made a set of tank experiments where he slid like a slot down a slope, and that generated a wave. The dropping of this interface here produces a downdraw of the ocean here, and the pressure at the front here pushes up the ocean. So you get a couple. His relationships tell you the amplitude above the source. So that's what I'm showing here. From all of our landslides, Yu-Chun has calculated an amplitude at source. According to Daniele Casalbori in Italy, he says that actually these amplitudes, even though they're from the source, they're not too different to what you experience at the coast. And so what you would expect, this is going to spread out. So as the wave front spreads out, it's going to lose energy. But as it gets into the coast, because of the shoaling effects and run up, it will increase in amplitude. And he suggests that in Italy, it turns out that they're not, those two effects kind of cancel out, which is a bit surprising. But anyway, so we take these as useful indicators of potential run-up, and we use them in a bit of a sense that you use magnitude of an earthquake. Magnitude of an earthquake also doesn't tell you the ground shaking. You have to do more to use it, but it does tell you roughly an idea of relative size. So we use it in that sense. And what it suggests is that they would have been perhaps 13 landslides that would have generated tsunamis of greater than 1 meter height if they were to occur today at present sea level conditions. We don't know when these happen. We're just assuming the present day conditions. And most of them would have been dangerous around St. George and Terceira. So although we're suggesting Pico and Fayal have a bigger earthquake risk, well, the tsunami risk might actually be larger for St. George and Terceira. So there clearly needs to be more work done on this. So we've been looking at the landslides high up near the shelf edge. Now imagine this going whoosh down slope, producing a sedimentary flow. We're going to look in the cores. And we thought before we did this that we'd see a lot of turbidites in these cores that reflected these many embayments. We teamed up with Tor Hanstein's group. Tor had a cruise in 2017 amongst the Azores, and they collected an enormous number of cores. We selected 4, shown by these yellow symbols, where it might be possible to link products of erosion, landsliding from an adjacent land. So we have these basins that are quite enclosed. What we're trying to do is to see if there's a record of all the material that's shed by the island, and what do we see in these cores. So we kind of naively thought this would be like a giant source to sink arrangement. We have the source nearby, we've characterized some of that. Now we're going to look at the sink and we're going to see if they compare with each other. Naivety is a good thing, I think. Maybe doesn't lead to what you expect, but gets you started. So I'm going to show, okay, this is one of the cores. I mean, when we turned up in Geomar, I was a bit horrified to see the actual core, because I couldn't see how on earth you can classify this. You see the layering, you see obviously the black sand, which is quite a good candidate for a volcaniclastic deposit, but it's quite hard to interpret it visually to work out what's going on. So Yuchen, working with our German friends, came up with a method where we used multiple sources of evidence, put it all together and arrive at a classification. And that include, okay, sedimentary structures, our assessment of grain size, geochemistry. If you had an eruption from a body of melt, you might expect it to produce glass of a very narrow range of compositions, and that's true of some of these. Some of them have a more diverse range of geochemistry, which suggests something else, perhaps. The mineralogy, some of the samples contain carbonates, for example, and that's a sign that maybe the flows involved sediment on the shelf or on the slope. We also looked at the shapes of the particles. So here, this is a deposit we think is a fallout deposit, and the particles are extremely angular. On the other hand, here we see the particles are much more rounded. So we have a measure of angularity, and we've used that to try to classify the sediment. Some of the sediment clearly has biogenic particles in. That's a good sign that it involved shelf sediment or slope sediment. So putting all this together, Yuchen and our German colleagues have classified the sediment into a number of types, and I'll move on to the results. Yellow here is the hemipelagic sediment. This is the slow, steady fallout of fine particles between events. The brown, the orangey brown, these are secondary volcaniclastic. So we think these could be originating from landslides. So they may have carbonate in. They may have, we also looked at organic carbon, and they tended to have finite organic carbon in, whereas the dark, these volcaniclastics had very low carbon. So the volcaniclastics we've separated into what are probably turbidites and fallout deposits. So we have this classification. It was extremely painful, I think, to go through, and Yuchen has done a lot of work here, and we had a lot of backwards and forth discussing these. So only 4 cores took quite a bit of time, but I think at the end of it, we have a very, very good data set. And maybe this could be done in other places too. The Azores are great because you have these basins very close to the volcanoes. So they're going to record a lot of the transport of material away from the volcanoes. But the question then is, how do you really compare different island groups? We're dealing with things that are very heterogeneous. And traditionally, we've dealt with it by looking at just looking at cores, I guess qualitatively, trying to describe how different they are. One possible way of comparing areas is to use a result that Hiscott published in '92. He looked at volcaniclastic deposits around the Isu-Boninark, and surprisingly, they had an almost perfect inverse power law between numbers of turbidites and their thickness, and it had a slope of -1. So maybe this is a useful way to compare different island groups. So what we've done here is to plot the number of turbidites, this is number per core length, against against the turbidite thickness. And you see most of our turbidites are around 10 centimeters. That's actually not too different to the Cape Verde Islands. It's quite different to Gran Canaria. Gran Canaria, there was an extensive coring program by the ODP, and Schminke and Sumita published some data we've used here. You see, it's a very different kind of graph to ours and the Cape Verde Islands. And it reflects, it simply reflects that the Gran Canaria eruptions involved very episodic, but very large, dramatic eruptions, which produce some very thick beds. And we haven't really detected so many of the thick beds in our data set. Maybe they do lie beneath the cores, but we have no way of knowing. The volumes, so we've worked out these volumes for these deposits, and it's interesting to then compare with volumes on land. So Tercera, for example, I'll show one of these graphs. Tercera, Pimento and others characterize an ignimbrite that was in place about 25,000 years. And we see this ignimbrite in our core as well. And their dense rock equivalent volume, plotted here, is actually not too different from our turbidite volume. What Yuchen has done is worked out a volume by taking the thickness of the sediment in the core and multiplied by the basin area. And he's also done the same, but allowing for thinning of the turbidite with distance. So hence there's a range here, not a single value. Well, either way, it seems this deposit is actually quite significant compared to the deposit on land. And if you see in the map here, a lot of the ignimbrite gets thicker towards the coast. So it's not surprising that perhaps a lot of it went off the north shore, down the slope, and is in the basin floor. So we can do these kinds of comparisons and try to fill in some of the gaps in some of these big eruptions. Now looking at the landslides, there aren't so many landslides in this particular core, but Yuchen's done a similar kind of calculation. When we compare the histogram of landslide embayments on the slope, so we go right up the slope and we look at these landslide embayments, there is an overlap. So it looks like we are recording the biggest of these landslides, but we're not seeing all the smaller landslides. And so I guess a bit of a surprise to me was that we don't see so many landslide generated deposits offshore. Again, come back to my naivety, I guess. And it looks like what happens probably is most of these smaller landslips produce a sedimentary flow of some kind, but it just deposits on the slope and doesn't make it as far as the basin floor. or some of it may be homogenized by bioturbation perhaps, but I think most of it probably just deposits on the slope. So this is all ongoing. We haven't published this, we're just working on it at the moment. We got funded to get some carbon-14 dates. So UCHN spent some of our lockdown picking out foraminifera from the samples we had, and we had them dated in Glasgow, the NERC facility, and we're plotting them here as calendar age, been converted to calendar age, versus hemipelagic sediment depth. So it's as if we've stripped out all the turbidites and fallout deposits, and we're plotting hemipelagic depth on the vertical axis and calendar age on the horizontal axis. And this line here is a reference site about 100, a bit more than 100 kilometers south of Pico, so it's away from the islands. And as you might expect, there's faster accumulation amongst the islands. So there's higher productivity of more biogenic production perhaps, and there's also all the finer particles shed by erosion from the islands. So it's not surprising. What is interesting is that there's this pickup in hemipelagic deposition rates towards the present day. So up here we've plotted the sea level curves, and so going into the Holocene, there seems to be a pickup in hemipelagic sedimentation. Down here, I'm showing the frequencies of emplacements of the turbidites. So the secondary volcaniclastics are shown in bold here. So we think these could be the larger landslides, and there is a higher frequency apparently in the last 8,000 years than the previous times. That's not surprising, perhaps. If you can remember back to my slide showing the offshore transport of sediment across the shelf, well, coastal erosion is higher today because the sea cliffs are exposed to waves. And we have biogenic production on the shelf. When sea level was lower, there wouldn't have been any biogenic production either. So there's more sediment produced today than was the case during the LGM, last glacial maximum. And so that's not, so maybe it's not surprising. We're exporting more sediment, so it's building up. And if earthquakes are occurring randomly as triggers, then maybe it's not surprising that we see this. What is surprising for me, and I don't know the answer really, is the primary volcaniclastic also has this higher frequency. I know it happens on Iceland, and there's a good reason for that because of the retreat of the ice led to decompression of the magma chambers. But I'm not aware of this being the case in temperate islands like the Azores. And of course, they may have had some ice, but I'll be surprised if it would be like this. So that's been our big surprise. So it's just a list of recommendations of what we think could be done in the future. There needs to be modeling of the tsunamis. If this is a risk, maybe it should be investigated. We think there's this risk of bigger earthquakes underneath 2 of the islands, and perhaps some of the big faults offshore ought to be investigated. We know nothing about the recent activity on the offshore faults. You could follow the active faults on land offshore. We could do with knowing the geotechnical properties of these slope sediments, and do it elsewhere. And question is, does this Holocene higher eruptive frequency hold up if we look at other cores? So we improve our statistical confidence. So to conclude, we found a large number of landslides around the upper slopes of these islands. Some of them may have a tsunami risk. There could be an earthquake assessment result here. most of the volcaniclastic sediments in these cores are primary. They're from pyroclastic flows and so on that have gone into the sea and fed turbidity currents fairly directly. Not many are landslide generated. Carbon-14 dates suggest that these, I haven't talked about this, but they're only they're not so frequent, maybe, these big events. I don't know if that means they're not to be worried about. George Walker was a famous physical volcanologist, and sadly he's no longer with us. I had the good fortune to meet him when I was in Oxford. He took the time to come and chat to me over some maps looking at the Azores. And he said, okay, the Azores are characterized by these frequent, many small eruptions, but also frequent earthquakes. And so they're kind of different from places like Hawaii. Have these very frequent activity. And for local people, this is potentially an issue. People don't seem to, when I visited there, they don't seem to worry about it. But I mean, as an outsider, I would be worried. You see in this picture, this is the commercial port of Horta in Fayal, and this is was the old harbour when they used to use wooden fishing vessels. This here is a volcanic cone, and I'm actually standing on a volcanic cone looking down on the village, on the town, and up to the left you have the caldera, the big caldera that produced an eruption. I can't remember, the C11 eruption, I can't remember when it was, but it's produced a deposit in our cores. And you can see how densely populated the streets are and how dense the streets are. So these islands are, studying the geology of these islands is important because people live here, and mitigating any catastrophe would be very difficult, as you can see from this photograph. And I think at that point I stop. Yes, thank you for letting me give the talk.